Hi everyone, welcome to Vedantu J English. I'm Diksha Kaushal, your chemistry master teacher, and very good evening to all the students here. So guys, this is a demo session of Sigma class, how we teach in Sigma class, right? So I have picked out some topics from structure of atom, and I'm going to do those topics, right? And this is not like I have picked up in sequence, right? Definitely not. So I have picked out 2-3 topics. One is general introduction about atoms, then Rutherford model, and the third one is photoelectric effect. Okay, so let's try to understand these 3 topics, right? How we are going to study in the Sigma batch. So everybody, this is my introduction. I am Diksha Kaushal and I have done BSc, MSc in chemistry and BEd, and I have 8+ years of experience. And I am here why students love me, because I teach every student. I treat like if you're sitting on the back in the class, right? For me, a teacher is someone not who is making a topper, right? A topper is eventually going to study, but to make that student who is not able to understand thing, to teach that student in so much detail that that student becomes a topper, I think that is the best quality of a teacher. That's why students love me, because I teach every student in detail, and no doubt we are in the online platform still, right? Don't worry, I'll make you feel like you are sitting in the offline class only, because I focus on every student here. So everyone, Parvati, Alan, Yogesh, Zoya, Jason, Alan, Vasuki, very good evening to all the students here. Let me know in the chat box, shall we start with the class? Everybody, are you ready for the class? Shall we start with the session? Okay, I'll start with a very basic thing, that is atoms, right? Not in a traditional manner, we are going to see what are atoms, right? So, right, we will play a game for atoms, right? So, we know that in an atom, inside the nucleus, you have neutrons and you have protons, right? Inside the nucleus, you have neutrons and you have protons. And mass, if you see, if you represent an element, right, that is represented by X, this is E, this is Z. Now, students, you will see that this E is the mass number. E is the mass number that is represented by what is there in the nucleus. In the nucleus, you have neutrons and you have protons, right? Then Z is the atomic number. And who will tell me what is there in the atomic number? Atomic number is represented by the number of protons, right? Now the question arises, ma'am, why it is so, right? Don't worry, we will study. We are studying that in detail in our Sigma batch, right? But here, right, I'll tell you one simple thing here. Because beta, when you talk about mass number, mass is defined by those things which have some value, right? So we know that mass of electron is 10 raised to power minus 31 and proton is 10 raised to power minus 27. Now you can see that mass of electron is very small as compared to mass of proton. That is why this electron that is revolving around the nucleus, that is totally neglected, and that's why we calculate a mass number with the mass of neutrons, or you can say number of neutrons plus number of protons, right? And why, ma'am, atomic number is represented by protons? Because we know that inside the nucleus, it's like someone will lock you in the room and you can't get out of the room. Neutrons and protons are in that condition, right? So that's why atomic number is represented by protons, not electrons, right? And if you talk about, ma'am, are protons equals to electrons? That is there only in case of neutral atom, right? If you have neutral atom, if you have any cation, let's say you are taking away the electron, right? You have taken away the electron. In that case, you can't say that electrons and protons are equal, because you are taking away one electron. So if you talk about a neutral atom, let's say nitrogen, 7 protons and 7 electrons, right? But if you talk about N negative, you will have one more electron. N2 negative, you will have two more electrons. But protons, you can't take out of that nucleus. that is locked in the nucleus. Is that clear? Right, everybody? Is that clear to everybody? A group of atoms that are bonded together in a chemical bond that are called molecules, right? That was molecule. Now let us start with the quiz. Okay. Before the quiz, let's play some game here, right? That's why we have the Sigma batch, because very small topics also here. So I am picking very general topic, right? We will proceed towards the complexity of the chapter also, right? So if you talk about a very basic thing, that is atom. On this, how we can understand and remember atom more, like more easily, we can play some game here. Like, let's play this game. Let's see who is going to answer me this here, who is going to answer this here. So the game is that here you have neutrons and protons and electrons are revolving around it, right? Let us see who will tell me what is that element. What is that element? I think the brightness is too much. I'll just decrease the brightness here, right? Okay. Now tell me, students, what is that element? Can you see it has 2 protons, 2 neutrons, 2 electrons? And the atomic number is justified by the number of protons. Because it has 2 protons, then we can say hydrogen, helium. So atom we are talking about is hydrogen, helium. So answer will be, is it a neutral atom? Whenever number of electrons and protons are equal, we will consider it as a neutral atom. Electrons are 2, protons are 2, it is a neutral atom. Check, done. Right? Check, done. Right? Let's play one more thing. Okay? Next one, let's see who is going to answer me this. Right? Protons, neutrons and electrons you have. Right? That is given. Protons is 7, neutrons is 8, electrons are 7. Right? Number of protons will tell you the atomic number. Hydrogen, helium, this you will study in the periodic classification. Hydrogen, like what is the atomic number, what is the element in that atomic number. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Nitrogen was the 7th, right? So answer will be nitrogen. Is it a neutral atom? Protons and electrons are equal, so it is neutron. Check, done. Right? Okay. Next one. Let us see who will answer this. Let us see who will answer this. Find the element. Protons, neutrons and electrons are given to you. Let us see who is going to answer this thing here. Let me see in the comment section who is going to answer me this here. Protons are 8, neutrons are 8. This is 8. 8 atomic number. Very good, Purvika. Very good, Purvika. Alan, very good. Yes. So here it is 8 protons. 8 protons is 1, 2, 3, 4, 5, 6, 7, 8. Oxygen, right? Is it a neutral atom or not? Number of electrons and protons are equal or not equal? They are equal. 8, 8. So it will be a neutral atom, right? Shall we do 2 more or shall we proceed towards the next game, right? Let's see what else we can, understand here, right? This is basically to tell you what is that and what is this, right? So this you can make, right? This even, I think they are wait a minute. Element is this, protons. Okay, check it. So here, this is not a game. This is for teaching purpose. That for example, you have 1 proton. That is hydrogen, right? And that is a hydrogen positive ion. Okay? Why? Because in hydrogen, can I add 1 neutron? No, right? If I am adding 1 neutron here, that will be the isotope of hydrogen. Because hydrogen itself do not have any, it will be deuterium, right? Okay, if I add 2 neutrons here, that will be tritium, right? And now if I'm adding 1 electron, that will be neutral atom. If I pick out neutrons here, that will be hydrogen atom. Let's say I'm adding 2 protons, right? This is helium positive ion. If I pick out 1 electron also from here, this is helium 2 positive ions. The charge is 2. Net charge is 2. As you can see, net charge is 2. Mass number you can see, it is 2. Hydrogen, helium, right? So now if I add neutrons also into it, right? I have added neutron. Mass number now has increased. You got it? That when you, in helium atom, the mass number is 4. Then why it is showing 2 here? Because in helium, you also have neutrons. Neutrons will correspond to the mass number. Now, this is helium 2 positive ion. Let's add electron. 1 electron, second electron, right? If I want to put third electron, can I put it here? 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 No, right? Because in 1s, there will be only 2 electrons. So that's why only 2 electrons I can put. Now, why negative sign here? Because you have added 1 extra electron, right? Because you have added 1 extra electron. So, similarly, you can make, let's say, one more, that is lithium. Now, lithium, you have 3 electrons, 3 this, and you can add one more neutron, because in lithium, neutrons is 3. Electrons, if I add one more, it will be negative. If I take out 2 electrons here, this will be positive. If I take out one more electron, this will be lithium 2 positive. One more electron, that will be lithium 3 positive. Got it? Clear? Any problem in this? Any problem in this, students? Is that clear to everybody or not? Is it an interesting way to understand things? Right? Okay. So, now, let us see the quiz here. Who is going to answer me the quiz? Right? Which prefix will be added to 8 number of atoms which attach to any compound? Right? Okay. If let's say you have which prefix with 8 number of atoms are attached, 8 number of atoms are attached, the prefix will be octa, right? The prefix will be octa, right? This should, chalo, let's do this, right? For this is for general atoms and molecules only. Identify which of the following is an example of atom, compounds and ions. Atom, compounds and ions. Let's see who is going to answer this. Atoms, this and ions. What is an atom? What is an atom? Helium is an atom. Right? First thing is example for atoms, compounds and ions. Atom is helium and carbon are atom. Yes, yes. This is not an atom. This is an ion. Ion is this. This is not an ion. Right? This is an ion. This is not an ion. These two are ions. And these two are compounds. So we can say A is the correct answer. Right? A is the correct answer. These are molecules which are bounded to each other. These are ions and these are atoms. Right? Which are not bonded chemically to anything. Right? Now, let us study J.J. Thomson atomic model, right? So, anybody, you have anything like what you can relate to? Do you eat watermelon? Do you eat watermelon? How many of you love watermelon? Without injections, of course, right? How many of you love watermelons? So, watermelons, that black seeds we hate, right? These are the electrons that we just throw out, right? And that red part, this is by J.J. Thomson, that the red part in the watermelon, that is the positive part. That is the positive part. That means we know till now, just understand one thing. When we are talking about protons, when we are talking about Thomson model, Rutherford model, till now there is no discovery of neutrons. They have no idea that neutrons exist. They only know that there is proton, there is electron. Now, what is the idea? Where you should put protons and electrons? They did a lot of experiments. Thomson, why he concluded this? Because experiments were going on, and what was being observed in the experiments, that electron you can take out, but proton you cannot take out, right? That's how he concluded that there is a large sphere, right? A big sphere in which red part, let's say watermelon, in which red part is the positive sphere, which you can't pick out like seeds, right? But seeds, those black seeds are electrons that will take part in the reaction and you can pick them out, right? That is the model of Thomson, right? So Thomson, who invented the electron in the year 1897, suggested that it is a plum pudding model. Plum pudding, like nuts you have, right? Or watermelon model, right? These kind of model, these are the name given to it, right? Propose that an electron consists of positively charged sphere and the electrons are embedded into it, like you have seeds in the watermelon. In magnitude, the negative and positively charged are equal. Why they are equal? Because can you see, the atom is electrically neutral. Iron is not electrically neutral. In atom, electrons and protons are same, right? That's how we concluded that. He concluded that the charges of protons and electrons are going to be same and opposite. The whole atom is electrically neutral. Both Thomson model explained, but Thomson model explained that atoms are electrically neutral, right? He explained that atoms, this is electrically neutral, but you know, then after that, so many experiments were done that were against the Thomson model, right? That's why this was ruled out, right? Now, Thomson model atom, you can see, can't overfill atomic orbitals, right? If you don't have any. So basically, uh, he was not able to tell that how electrons are, he just said that they are embedded into it, right? Then how come you can say it is stable, right? The stability of the atom he was not able to explain, right? So, now let us see Rutherford model, right? Rutherford model, that is the gold leaf experiment. He used gold, right? Gold is so expensive, still he used that, right? So J.J. Thomson devises plum pudding model and Rutherford gold leaf experiment. I am about to end man's whole career, right? This you will see in chemistry, right? In periodic classification, you will see this. One will give some like theory, someone else will come and they will say, this is wrong, I am right. Okay. So we will study a lot of drawbacks, demerits, right? It doesn't mean that Thomson was a loser, right? No. At that time, thinking that atom is a sphere, right? And electrons and protons are equal, it is electrically neutral, that was also a big deal. That's why it is in your NCERT, right? But now he was not able to explain so many things. That's why Rutherford came into picture. Now, Rutherford model was not something that was totally related to. Wait a minute. Is this clear? Wait a minute. Let me see. That is clear. Chalo. Now, let us see the Rutherford model. Instead of telling you from this experiment, chalo, I'll tell you the basic of this experiment. Actually, Rutherford was not intentionally doing this, right? So, in the lab, right, workers were working on something else. Then they found out something, right? Some observation they found out, right? What they were doing exactly, they had this radioactive source, right? From which alpha particles were getting scattered, right? So alpha particles, what is an alpha particles? Anybody in the chat box? What is an alpha particle? What is an alpha particle? Helium 2 positive. You have helium ion, you take out 2 electrons from it, that is called alpha particle, right? Okay, that is called alpha particle. So helium 2 positive, that means alpha particles are positive in nature. Now, when alpha particles will pass through this thing, this pleats, these are there so that we can have only one sequence of alpha particles here, right? Less alpha particles so that we can observe something out of it. Now, here you will have the gold foil. This is the gold foil, right? This is the gold foil, right? It should be yellow in color, right? So this is the gold foil, and here this is the zinc screen, that is the fluorescent screen, because you can't like observe with the naked eye what is happening, right? So the blinking or the ZNS screen will tell you what exactly is happening here, right? So now what you will see here, that so many observations were there. I'll just tell you with the help of the experiment only, right? Let's do this. Let's study this experiment only, guys. Okay, let's study this experiment. Chalo. Now, I'll make protons very less, okay? Very less protons. Let's say you have hardly 20, 24 protons. Neutrons also somewhat in the same range, right? We will start with the lightest metal, right? Okay. Then energy, let's say I want traces. Traces means I'll tell you alpha particle is there, right? Alpha particle, and this is the gold foil atoms, right? This is, I'm assuming that these are gold foil atoms. If you're talking about gold foil atoms, then it should be very, very heavy. So let's make it heavy. That means the nucleus is heavy now because it has more protons and more neutrons, right? So this, if you see, these are the atoms, right? Okay. This is the experiment, right? This beam of alpha particle is passing through this gold foil which has atoms in it. Now there are different observations that some of them are passing straight, some of them are deflecting, some of them are bouncing back, right? That I want to show you with the help of this experiment here, right? So here what you will see, when I pass the alpha particles, right? See, in this, so I don't think so it will be that much visible to you. Let's see the traces here, right? With traces, what you will see, can you see this here? Some of the alpha particles are moving straight. Most of the alpha particles are moving straight. Some of them are being deflected. Some of them. Why only some of them are being deflected? Because the nucleus is very, very small as compared to this atom. The nucleus is very small. That is the reason only some of them that are very near to the nucleus, only they are getting deflected here, right? Now, you will see very few, like 1 in 20,000, right? They will bounce back. Till now, though, I have not seen anyone which is bouncing back. This one was bouncing back. Can I see anything which is bouncing back? That one was bouncing back, right? Very rare that are bouncing back, isn't it? Very rare. That was bouncing back, right? This is bouncing back. Very rare you have which are bouncing back. Most of them are moving straight, right? Some of them are being deflected. Very rare are bouncing back. Now, ma'am, what is the reason behind that? Okay, what is the reason behind that? Let's see that. See, I'll just show you the diagram. Okay, here only, right? See, this is the nucleus, right? Understand one thing. If I talk about a nucleus, okay, where should I make the nucleus? Okay, I will make the nucleus here only, right? So this is the nucleus, right? If this is the atom, let's say the nucleus is very, very small, right? Now, what exactly is happening? Because the alpha particle is a positively charged particle, so it will get repelled by the positive charge. So when you pass it through, right, when, let's say, because most of the space inside the atom is empty, that's why it is passing very easily. Here also it is passing very easily. If you have a alpha particle that is passing very near, so it will get deflected. Alpha particle that is passing very near, it will get deflected. That's why only some of them are being deflected. But 1 in 20,000 will actually strike the nucleus and it will bounce back. Okay, this is happening here. Understood, everybody? This is happening here, right? Okay, everyone understood? Now let us see the observations and conclusions that we can make from here. First is, according to Rutherford atomic model, the positively charged, because most of the alpha particles, as you can see, that most of the alpha particles are going straight. Okay, if I increase the speed, right, you will see it more often here, that most of the alpha particles are going straight. That means most of the space inside the atom is empty, right? Now, some of them are deflecting. That means only some of them are very near to the nucleus, right? But if it is even near to the nucleus, it will deflect. That means the positive thing that is inside, that is in the center of the atom, that is very positive, right? That is why that is positive, that is why it is deflecting, right? Now, third observation is, only 1 out of 20,000 is bouncing back. You can see only one. You will see, I'll just show you something here, right? This is deflecting, this is deflecting, this is deflecting, right? In this area, is there anyone which has bounced back till now? Let's see, let's observe, I told you 1 in 20,000. So we have to wait for the one which is bouncing back. Okay. Still, to abhi tak to there is nothing which is bouncing back, right? I'm still waiting. See, That's what I am telling you, that 1 in 20,000 will bounce back, right? That will strike here, here, or here, that will bounce back, right? Okay. That is also got deflected, right? Very few. See, this also got deflected, this also got deflected, this also got deflected, this also got deflected. Only one out of that 20,000, it will take us time. Oh, that was being bounced back. Did you see? Okay, there was one which was bouncing back. So, very like 1 out of 20,000 will bounce back. The reason is because this positive charge is very small. But if you strike there, it is so dense that it will bounce back the alpha particle. Okay, so that are the observations as you can see it here. According to Rutherford, the positively charged particles and most of the atom mass is concentrated in the minimum volume, that is the nucleus. He called this region nucleus. And if someone asks you who discovered nucleus, Rutherford, right? Then negatively charged electrons encircle nucleus of an atom. Negatively charged particles, they will encircle the nucleus, right? And Rutherford also proposed that the electrons move at the speed of light around the nucleus. He named these circular paths the orbits, right? No doubt this theory also went wrong, and that's why we have new theory, that is Bohr atomic model theory, that we will learn in the batch, right? Okay, so don't worry about that. That is going on in the batch. Let's see who is going to answer these questions, right? Okay. Let us see who is going to answer these questions. Which of the following model of an atom describe positively charged sphere of the matter with a negatively charged electron? Positively charged sphere of matter with negatively charged electron embedded in it. That is by which thing? By Thomson model. So answer is A, Thomson model. How did the actual results of gold foil experiment differ from the expected result? In reality, they were not expecting this. There was no difference. That is absolutely wrong. Rutherford expected particles to travel through the atoms, but instead they recoheted and rebounded in unexpected direction. The alpha particles called gauze were to undergo nuclear fission. This did not happen. None of these answers are correct. So basically what happened? Rutherford expected that, okay, the alpha particles will move straight, but in reality, some were being deflected, some were bouncing back. So that was the new thing, right? So answer will be D is the correct answer. Very good. Okay, next. Rutherford realized that atomic nucleus was positively charged, right? Rutherford realized that atomic nucleus was positively charged. It attracted how? It attracted alpha particle. It deflected alpha particle. It had no effect on the alpha particle. It produced alpha particle. That is absolutely wrong. It had no effect. That is also wrong. Now tell me, it attracted the alpha particles or it repelled or deflected the alpha particles? It deflected the alpha particles. We can see, no, this is positive. This is also positive. It is coming. It is going to deflect it, right? So it deflected the alpha particle, right? Okay, students, that is clear to everybody or not? If there is any problem, then let me know in the chat box. Anonymous, Puna, Nikit. Yes, students, any problem till here? Any problem till here? Now, next is photoelectric effect. Let's understand photoelectric effect, right? Let's understand that. Okay. Photoelectric effect is basically you have a light. Okay, tell me, light is made up of which thing? Light is made up of which thing? Light is made up of photons, isn't it? Light is made up of photons, right? So those photons, there is a metal plate, right? Those photons will strike the metal plate. So it's a very simple way, right? I'll tell you this, the way. So in a very simple way, we are going to learn this, right? You can understand this. You and your friend wants to go out, right? So you want your friend to take permission from your parents, right? You and your friend wants to go out on a trip, right? You're like, let's go out or on a trip maybe, or maybe say you want to go out, right? Now, this is, let's say, friend number A, right? This is friend number B. Okay, this is friend number A, this is friend number B, right? Now this friend number A and B, they both want to go out. And this friend B and this A's parents are very strict. Okay, so this B has to take permission from the parents. Definitely, yeah, you have to take permission from the parents, right? A parents are like, we don't want this person to go. We don't want our kid to go. B is like, you will have to go, otherwise I will not go, right? So you have to ask their parents, right? You have to convince the parents. Now, three possibilities are there. What are these three possibilities? One possibility is that B is able to convince the parents, right? First possibility is B is able to, let's not name it B, let's name it Chintu Mintu. Okay, this is Chintu, this is Mintu, right? And these are the parents of Chintu, right? So Mintu is like, okay, I'll ask your parents, right? Mintu is like full, like, okay, I'm such an ideal person, I'll go, right? I'll convince the parents, I'll say, okay, I also got 95% marks, please let him go, right? We will enjoy, but we will also focus on the exams, right? It's very important to refresh yourself, this and that, all these things he was able to convince the parents, right? And the parents were like, okay, you can go. This Mintu seems very genuine and very sensible guy. So I can send Chintu with Mintu, right? So it's the image of your best friends with your parents, right? Such an amazing guy. What you're doing nothing in your life. And your Mintu will like, oh, I am also not doing anything in my life. It's just that I'm good. Image is good, right? So image of Mintu is good on parents. That's why parents are like, you can go out, right? So he's able to convince the parents. Second is, Chintu is like, convince my parents, they are very strict, right? Mintu be like, I'll be able to do it, don't worry, right? Mintu be like, okay, I am such a good person, this and that, I'll make him study, this and that, will also study on the trip, right? Still the parents were like, okay, I will not agree. But at one point, the parents were like, okay, we can send him along with you, you can tag along, but this money we will not give, right? You can go, but pick out the money from your piggy bank, right? Money, maybe you have 1,000 rupees, 2,000 rupees, pick out that money and go on a trip, right? We are not going to give you the money, right? Third possibility is that Chintu is like, hey, my parents are very strict. Mintu will like, don't worry, bro, I am like full chill, right? Mintu is overconfident. He's like, okay, don't worry, we'll study also, this also. But parents were over clever. Parents were like, no, we know you are just acting in front of us. You're not going to study nothing. You're going to waste your time. So parents were like, okay, you can't go, right? So three possibilities are possible. Is there any other possibilities, right? Is there any other possibilities? No other possibilities, right? So same thing here will happen with the electron, right? So what you will have here, guys, I'll just show you this with the help of this diagram. Okay, so I'll just show you this with the help of this thing here, right? This you can stop, right? Okay. Can you see this here? Can you see this here? So, bacha, this is the voltage. This is the metal plate. This is the metal plate. This is the metal plate in which incident light we are throwing. This incident light is Chintu, Mintu or parents. This incident light is Mintu, right? This metal plate is Chintu, right? And you are going to take the electron. You are going to take the Chintu out of this metal plate, right? Metal plate is basically the house. And in this house, you also have parents, right? So parents, and this is the house, parents and Chintu are sitting here, Mintu will come, right? Mintu will be like, hey, if it is able to convince, that means electron will be ejected with the kinetic energy. Electron will go out with having money from the parents. Parents are like, okay, take 2,000, enjoy, right? Parents are so convinced, right? So if min2 has more convincing power, that means if min2 is very like more convincing power means if min2 is like, bro, I can convince, I have more energy, right? That means if the energy of min2 is more than the strictness of the parents, right, then easily it can take out the chintu, take out the electron with the money, that means with the kinetic energy. So in simple chemistry words, if you give the incident light, those photon, if they have more energy as compared to the energy of the electron, right, then electron will be ejected with the kinetic energy, it will also move, right? But if the energy of the incident light is equal to the energy of the electron, that means electron will be ejected out, but it will not have any kinetic energy. If third case is, if the incident light has no energy, the convincing power is very low, right? Chintu will stay at home only. Electron will not be ejected here, right? Electron will not be ejected here, right? Can we just see this the simulation here on this screen, right? The topic is clear to you what is happening here, right? Okay, so let us just see that. Let's talk about sodium, right? So here what we are going to do, let's start it, right? I'm going to start it here. Wavelength, you can take any wavelength, right? So here I'll take less wavelength, right? Beta, this also I'll tell you everything. What is the relation with the wavelength? Right now, though, I have just told you one thing, that electron is ejected. Now we will see the variation of voltage, everything here, right? Now I'm keeping the wavelength less. Okay? Tell me one thing. E is equals to h mu. Ma'am, why this happened? Why on changing the electron, why on changing the lambda, energy is increasing? E is inversely proportional to lambda, right? Now, if you see, lambda is less in violet color, that's why energy is more, right? So when you increase the lambda increases, you can see lambda has increased, right? Electron ejection has stopped, right? Here lambda is less. Lambda less means energy will be more, right? Energy will be more. Now let us see this thing here. Lambda, you will keep it as less only. I have kept it as, if I keep it in UV region, it will be very fast. Very, very fast. You can see very, very fast. If I keep it in the visible region, this much lambda, right? So here what will happen? This energy, what I am changing, can you see what I am changing? I am changing the energy of the incident light. That depends on which photon you are using, which lambda. As I told you, that lambda is inversely proportional to the energy. What I told you, energy and lambda, E is equals to hc by lambda. Do you agree? E is equals to hc by lambda. That means if lambda increases, energy decreases, right? If lambda decreases, energy will increase. Energy, we are talking about the energy of the incident light. Energy of the incident light should be more. More is the energy of incident, less is the lambda, more is the energy of incident light, more easily it can take out the electron. Can you see? More easily it is taking out the electron. As the lambda is increasing, energy is decreasing. So that's why the speed is also less, right? So that's how on variating the energy, you can see that how electrons are changing, right? I'll keep it at now at fixed at violet only, right? Now, if I keep the incident light frequency constant, now I'll just do one more thing here. That is, you should also know the formula here, that E is equals to W naught plus kinetic energy. Kinetic energy is the motion of the electron, the way they are moving, right? So if I see this here, E is equals to, let's say this is H mu is equals to H mu naught plus kinetic energy. Can you see this here? That H mu, this is the energy of incident light, right? That's why when I was decreasing the lambda, the energy of incident light was increasing. But this electron, it's dependent upon which atom you are using, which metal plate you are using. This is the energy of electron, and this is the kinetic energy that will be left, right? Firstly, we are variating the, let's keep the energy of the incident light fixed. That means this energy is fixed, right? Now, if I change one thing here, let's say if I change the metal, if I change zinc, right? Can you see it has changed? That means zinc has more energy, as that means zinc electrons require more energy than you are giving here. So that means this also you have to increase. This also you have to increase. Now we are giving it UV 215 nanometer of wavelength. Now energy is increasing. That's why with this UV range, it is able to take out electron even from zinc, right? Now, if you decrease it, if you decrease the energy, nothing is happening. Let's change it to copper. Copper, let's see if it is doing it. No. Then we again have to decrease the wavelength so that energy. At this point, it is able to take out the electron. Again, we will do it for platinum. For platinum also, platinum, even this much energy is not enough, right? For platinum, you need even more energy, right? Even more energy, only then it can take out the electron. These electrons are there only. Why? Can you see this very interesting thing here? These electrons are still here. These electrons are still here. Why? Because these electrons that are still here, they were ejected with the lower energy. Okay, I'll show you again. Right? Let's keep this here. You are taking out the electron, taking out the electron, taking out the electron. Right? Very slow energy, very slow energy. Or you can just even, okay, taking out the electron with very slow energy, and suddenly, very slow energy I'll talk about. Very slow energy, you're taking out the electron, right? Okay, with very, very slow energy. Why the energy of this electron is very less? Because this h mu naught, the work function, that is called the work function of the electron, how much work you need to do on the electron to eject it out of the metal, right? That is very high, right? That's why the incident light also you need is high. Only then it can eject out. Now, if you want the kinetic energy, why it is so less? If your incident light energy is not very high, kinetic energy will be less. If I increase the energy of this incident light, kinetic energy will increase. Let's see how. I increase the energy, right? You will see it has increased. Still, those few left were going very slow because they have the energy of the previous incident light, right? Got it, students? Now, you can also change this to calcium. Calcium is like totally crazy. Calcium is like, are you crazy? I am also happy with this energy. I'm also happy with this energy, right? I'm also happy with this much energy. I'm very slow. But sodium, let's see sodium with this much energy. Sodium with this much energy will go totally crazy, right? Sodium with this much energy, you will, like, in the blink of your eye, electrons are being ejected. Reason being, because now incident light is very high. Incident light is very high, right? You're giving UV radiation, very high, very less lambda, very high incident light. And here, the electron, the work function was less for sodium, and still you are giving it very high. That's why kinetic energy of the electron has increased, right? Got it, students? Right? Okay. Understood? Everybody, now let me know in the chat box if there is any problem in understanding what we are doing here. We have variated the work function. We have variated the intensity also. Now I'll fix these things, okay? I'll just fix these two things. I'll fix the intensity also. I'll fix the metal also, right? Now, can I change the current here, right? I can also change the current. Wait a minute. Oh, current versus this we want, no? So let's see this. How do I change the current here? Hmm. Current is at now fixed at 0.77. I wish I could change that. I don't know how to change it here. So no issues. I'll tell you like verbally what you have to do here, right? So this is clear to everybody, right? That it depends upon what is your, so this is your work function that I'll write by W naught, right? W naught is a work function or threshold energy, is property of the material which is defined as minimum quantity of energy required, right? Minimum energy that is required by the electron to get ejected out of the metal, right? Threshold frequency, energy work function, this work function is mu naught, W naught, that is H mu naught. So this mu naught is called the threshold frequency, and this Hc by lambda naught, this lambda naught is called the threshold wavelength, right? Okay, and this is the formula. E is equals to W naught plus kinetic energy. This is H mu, this is H mu naught. You can also write it as H mu naught. This is kinetic energy of the photoelectron that is being ejected out here, right? Okay, yes. So when photon of energy, that means the incident light is greater than the incident light, what you have to do? Electron has to get out, right? Electron can't stay lazy here, right? When the photon of energy is greater, incident light is greater, then the electron has to get out of its seat and move, right? And electron cannot just sleep like, okay, I'm chilling, right? So electron has to get out of its seat, right? Now let us see the variations here. What is stopping potential? All these things. Stopping potential is if you want to put external pressure, external potential to stop the motion of the electron. That means it is kinetic energy is equals to charge into Vs. That is the stopping potential. Vs is the stopping potential. Q is the charge. Charge for electron is E. So you can say that kinetic energy is equals to E into Vs. Vs is the stopping potential. Potential required to stop the removal of electron from the surface of the metal when incident light with energy greater than, that means H mu is greater than, wait a minute, yes, H mu is greater than H mu naught, but still you have to stop it. You have to stop it, right? Still you have to stop it. Energy's incident light is greater than the surface of the metal, the electron, the threshold frequency, right? The incident light frequency is greater than that, but still you have to stop it. That external potential is called stopping potential. Now let us see the variations. Let us see, understand these two graphs here, right? If you see this graph, effect of frequency on photoelectric effect. So this is kinetic energy and versus frequency. This is energy maximum, right? What you will see when you are increasing kinetic energy versus the frequency. See, one important thing, whenever you are increasing the frequency of incident light, kinetic energy will increase. Can you observe it here? I'll also give you the reason. When you increase the frequency, frequency means lambda will decrease. When you decrease the lambda, can you see the kinetic energy is increasing or decreasing? It is increasing. Can you see? Let's see, you move it here, right? Okay, there is no ejection of electron. Lambda decreases means frequency you are increasing. Frequency you are increasing. That means what is happening here? You are increasing the frequency, energy is increasing, right? So that's why, and why we have started it from mu naught. Why we have started from mu naught? This is not V naught, this is mu naught. Because at least this much frequency is required, no? Energy will not start from zero. If you see this here, at green light there is still something, at yellow light there is nothing. I'll just let these go, right? At yellow it is nothing, right? Okay, now we will see this, wait a minute. Current is also zero, no movement of electrons, right? When the electrons will move, current will increase, right? So you can also draw it with like current linear graph is there. You can also draw that, right? Now, as I'm increasing the frequency, there will be one point. Oh, this is that point. This 527 nanometer is that point where electrons are being ejected. That means the minimum frequency we have achieved, right? That's why while drawing the graph, we'll start the graph with the minimum frequency. Because before that, there is no ejection, there is zero kinetic energy. But after we have achieved this minimum frequency, then the kinetic energy will start increasing as we increase the now see the speed difference. Now you see the speed difference increases further. Now you see the speed difference increases further, right? Now you see the speed difference increases further. And this much is so like totally crazing. Electron like I am going crazy, bro. I have to run like I am in a marathon, right? So electron is like right now electron is like, I'll tell you simple thing. At this point, electron is like when students are in the first year of their 11th class, right? And this is electron one day before the exam, isn't it? This is electron one day before the exam, totally going crazy. Like, I don't know what to do. I so much syllabus I have, this and that, right? So that's how you can see this and draw this graph. Okay. Now, next one is the electron current and light frequency. Let's see that and understand that here. So light frequency, you are increasing with the help of that current is increasing. What is happening here? See, if you are seeing that light frequency, after this it is increasing. I'll just show you that here, right? Let's see this here. Let's see this here, right? Let's see this here. Okay. So here, wait a minute. Yes. If you see this here, right, the current at one point, right, it will become constant only, right? If you see this here, this is, wait a minute. Let's see, you have sodium. Let's see here. Okay, nothing, right? 0, 0, 0, right? It is increasing. Can you see it is increasing? It is increasing, right? Increasing, right? Increasing. Then it will start decreasing because at one point in the end it will become constant only, right? Okay, it will become constant only at one point, right? Now let us see next one, that is graphs of light intensity and electron current. Light intensity and electron, then what? So let us see with the light intensity what will happen. That means if you decrease, let's fix the wavelength here. Let's fix the wavelength. If you decrease or increase, right, that's how it is changing. If you decrease, right, intensity is 0, no current, right? As you increase the intensity, right, the current will increase. Now, can you tell me what is current? Let's see, what do you mean by current? Current means the number of photoelectron ejected. Interesting part is that when you increase the frequency, light frequency, there is no effect on the number of ejection of electron. That means, let's say Mintu is very powerful. He is able to convince. It's not like Mintu is like, I am very powerful, I'll also take his siblings along with him, right? Mintu can take only Chintu. That means one electron can take only one photon, right? And when you increase the frequency of that photon, it's not like, increase the frequency of that photon, it's not like it will take 3-4 people. No, it was there to convince Chintu, it can only take Chintu. That means even if you increase the frequency, it has no effect on the current, right? Even if you increase the frequency, it's not like number of electrons will be more ejected. If the frequency is increasing, the kinetic energy will increase, right? the money that is given to the Chintu, that will increase. It's not like Chintu will be like, hey, hi, Semu, Temu, Gemu, you also come along with me. No, right? That will not happen, right? Only one electron can take out only one photon. Remember this. If your frequency is increasing, number of photons ejected will increase. That's not possible. But if your light intensity, that means number of photons are increasing. This means number of photons. If your number of photons are increasing, then the electric current will start increase. One photon will take one electron, right? So more the number of photons, more the electric current, more will be the number of electrons ejected, right? Now, this is frequency with stopping potential. Stopping potential is the external potential that is applied, right? Now, what you will see, as you increase the frequency, right? See, simple thing is, if I increase the frequency, what I have to do? More kinetic energy is there. That means more stopping potential I will need. Simple is, if more frequency I have, more kinetic energy it will have. Let's say the frequency is this thing, okay, very high frequency. Now you will see the kinetic, these are which were rejected before only, okay. So let this person go, right? It's very slow. Right now also it's very slow, right? So as you can see, as lambda is decreasing, energy is increasing, energy increases means kinetic energy will also increase. That means to stop this, you have to apply very high voltage here, right? So that's why the stopping potential will also increase here, right? The stopping potential will also increase here. Was that clear to everybody? Right? Okay. Now, let us see the next one. That is, you have photoelectric current, and this is your zero. This is anode potential. This is retarding potential. Now, they are saying that when you're decreasing the potential, when you're increasing the potential, right? So, this is at zero. At zero, the photoelectric current is okay. But when you change the potential here, right, what will happen? What will happen? The photoelectric current will start decreasing, right? And when you increase the potential, right, then what will happen? The photoelectric current will increase, but there will be a saturation point. To more than that, the current cannot increase. That's a very, very important point. And this one is very tricky also, right? Because you know, this, if you see this from this thing only, right? If you see this, I don't think so. There we can change the potential. Chalo. What I'll do, I'll make the potential negative, right? Let me see if I can do that, right? I'll make the potential minus 2. Okay, make it minus 2. Now, what you will see, when the potential is less, right? When the potential is in the negative, then the current has to decrease. Let us see if it is decreasing. With the same this, right? With the same this, let's take this. Beta, what you are observing here? Can you see this thing here? When you're decreasing the potential, the current, how it is decreasing? The electrons are not able to go here. The electrons are stuck here. They are like playing in this ground only, right? Let's say, ma'am, you please increase the frequency so that energy can increase. Can you see even now some electrons are going back? Even now some electrons are going back because the potential is now minus 2. I have decreased the potential to minus 2, right? So when your potential is retarding, you have negative potential, right? What you will see that, let's change the frequency also. At some frequency, you will see that electron will start moving backwards. That means the current will decrease. Let's maintain this. Let's say I maintain this frequency. Now I will not change the frequency. Okay, now I'll only change the voltage. This is minus 2. At minus 2, let's see what happens. This is happening at minus 2, right? And minus 2, you have a lot of positive potential here, right? And you have negative potential here, right? Because this is positive, this is negative, it will start attracting, the current has decreased. Let's decrease it even more. Let's decrease it even more, right? Let's decrease it even more. What do you want me to do right here? Let's decrease it to -5. Okay. Let's decrease it to -5. Let us see what will happen now. No current, no current, right? No current. Can you see they are not able to strike here only? Then how can current will be there, right? Now, if I increase the positive potential, now I am going to increase the positive potential. Let's say I am increasing up to 5. Okay, firstly I'll increase up to 2 only, right? Firstly I'll increase up to 2 only. Let's see what happens now. Current is increasing, right? See, frequency I am not changing. Now I'll increase it to 5. Okay, I'll increase. Can you see current is 0.161. Now I'll increase it to, let's say, 3. If I increase it to 3, let's see what happens. Right? Current is increasing, current is same. So let's move it to 5. Okay, let's move it to 5. Let's see now. Now also current is same. Now let's move it to 10. Now also current is same. Can you see? When I'm increasing the positive potential, there is saturation point. More than that, nothing we can do. More than that, nothing we can do now. Okay, ma'am, can you show us the increment of the current? Okay, let's put it as 0. Let's put it as 0. 0 volt. Let's see the current. Let's see the current here at 0 volt. Sure. 0 volt, this is the current, right? Okay. I hope so they are giving the right current. We can even change this here. Let's change it to this one. Okay. So now this is at 0 voltage. Let's see if at 0.02 you can write, right? 0.02, you will see either it will be constant or it will increase, right? Now let's put it as 0.03. It is 0.256, 0.04. Okay. Now it is remaining constant only. That means we can say that when you increase it, it is almost constant, right? It is not increasing. But when you retard it, the current will start decreasing. When you retard it, that means when you give it negative potential, right? I'll again give negative potential in front of you, right? So that you can understand this. Let's say you are giving it negative potential, right? Can you see what is happening here? Current is 0.247. Now, if I start giving more negative potential, let's say I am giving it -2. Current is 0. Current has decreased here. Can you see how current is decreasing? Can you see that, students, that when you increase it, it remains constant almost, right? It has a saturation current. But when you retard it, it will start decreasing, right? Okay? Okay, everybody. This also they can ask you. This is mu3, this is mu2, this is mu1. This is, in this case, right, more the value of frequency, then if you provide it, let's say, this is, we are talking about potential, na? When you decrease it. Okay. So this will be that means mu3 is going to be greater than mu2 and mu3, because here kinetic energy more is needed. That's why this will be on the lesser side, right? Okay. Yes, students, everybody. Now next graph is again on the same plot, that is retarding potential. This is collector plate potential, right? Now here what you will see, that when you have stopping potential, when you give more than stopping potential, right, then what will happen? The current at point will firstly increase, then it will start decreasing. That will be your saturation current, right? This is the stopping potential, right, that is needed to stop it, right? When you provide more than the stopping potential, right? So what will happen? This is your current. Let's say at 0 you have this current, right? You are providing, let's say this is the current at zero potential, you have zero potential. This is the current that you are getting, right? This is the current. Let's talk about this one. This is the current that you are getting. You start providing the potential. As you start providing the potential, what you will see, the current is going to decrease because you are stopping the electrons here. When you provide more potential, the current is going to increase, but at one point it will remain the constant, because stopping potential is to stop the electron. When you stop the electron, the current will eventually stop here, right? Okay, students, everybody, right? So let's see this JEE main previous year question, right? Two questions we will do, and then we will then the class will over, right? When the light of frequency, the question is when the light of frequency twice, now what is that? Light of frequency twice the threshold frequency is incident on the metal plate, the maximum velocity of emitted electron is V1. Okay, maximum velocity of the emitted, that means kinetic energy, you can see from here. When the frequency of the incident radiation is increased, incident radiation, it is increased to 5 times the threshold value. The maximum velocity of the emitted electron becomes V2. Okay. When the frequency of incident light, that means mu is increased to 5 mu, then here velocity is V1. Sorry, here it is V2. And in this case, the velocity is V1. Right? They are asking you if V2 is equals to x of V1. You have to find the relation of V2 and V1, right? Then you can easily answer this, right? So now we will try to find the relation of V1 and V2, and then we will answer it. If you see, we know that you can just solve it like this also. So I'll solve it here also, right? We know that H mu is equals to H mu naught plus of half m V1 square, right? Because that is the kinetic energy of first one, right? Kinetic energy of the second one, that is going to be H mu dash is equals to H mu naught. Naught is constant, work function is constant, half m V2 square, right? Now V dash is equals to 5. So this will be 5H mu. Right? This will be 5H mu, right? Okay. Now we are going to write it here, right? Wait a minute, is acha, when the light of the frequency twice of the threshold frequency, that is also amazing. If we are saying that, that is also nice, that if we are saying that mu is equals to 2 mu naught and mu dash is equals to 5 of mu, that is given in the question, 5 times the initial frequency of 2 of mu naught, so it will become 10 of mu naught, right? Now you can put it here. Here answer will be, now if you put it here, this will be 10 of H mu naught. This will be 2 of, this will be H mu naught only. This will be 2 of H mu naught, right? Plus of half mv square, right? Plus of half mv square. Now they are asking you to find the relation of V1 and V2. See, you have H, you have mu naught. You can easily solve these two values here. This will be equals to H mu naught is equals to, from here, you can see that if you solve this thing here, right, I'll just put it here only, right? So I'll just solve it here only. If you solve this, you will get H mu naught is equals to half mv1 square, right? This will be equals to 9H mu naught is equals to half mv2 square. You divide this will cancel out, this will cancel out, mu naught, HH will cancel out. 1 by 9 is equals to V1 square by V2 square, right? Okay. 1 by 9 of V1 square by V2 square, right? Then this will be V2 square is equals to 9 of V1 square, right? If you take the under root, that means V2 is equals to 3 of V1, right? V2 is equals to 3 of V1 and X value will be equals to 3 here, right? Why it is coming out to be 2? This is q h mu naught. This is h mu naught. Keep it here. This will be h mu naught. No? This will be 9 of h mu naught. Half will cancel. Answer will be 3 only. Na? What is yours coming out to be? Mine is coming out to be 3, right? So if I have not done some silly mistake, then right now next question is the work function of some metals, these are given to you, is listed below. The number of metals which will show photoelectric effect when light of this much nanometer falls on the metal, right? So now this you have to calculate. From this you have to calculate h mu, that is the energy, right? Now you have to calculate the energy in the electron volt. Because this is given in nanometer, you can easily apply this formula, right? You can convert it into Armstrong, right? You can easily apply this formula 12400 by lambda, right? Then you can easily calculate the energy in electron volt, right? What you have to see, this energy has to be, because this is the energy of the incident light. If this is greater than all of them, like whichever of them out of them it is greater, that will show photoelectric effect, right? After solving, you will get the answer as 4.14 electron volt. Now the energy which is greater than 4, right? That means energy greater than 4.14, right? 4.14, this will not show, this will not show, this will not show, this will show, this will show, this will show. That means copper, silver and iron will show you the correct answer. Okay, these will show you the photoelectric effect. These kind of questions, students, we will solve in the batch, right? For one topic, for like in one session, one or maximum 2 topics will be covered, right? In detail. I have taken still less quizzes, right? In the batch, we are taking more quizzes, more questions, and after the class also you'll be provided with the DPPs, right? DPPs means, for example, I have completed Rutherford model today, photoelectric effect today. So the DPPs will be based on these effects only, right? These topics only the DPPs will be based on, right? We will give you the link of the DPPs, right? Every topic will have its own DPP. And then after the class, you can solve that DPP. And we will also give you in the Tattva modules will be provided to you. That are the Vedantu modules. From those modules, we will give you the questions that you will do from the given topics, right? That are most important questions. And then we will also give you the questions like, okay, these are not like, you can say these you can do for practice, right? So some questions will be MID, that is most important questions. Some questions will be for your practice so that you can practice more and more questions from there, right? Some questions will be the previous year questions from different subjects. So all the collections or practice questions we will give you for homework, and there will be doubt sessions also. And you know, in class doubt solving also will be there, right? You can ask the doubts in between the class, you can raise your hands in between the class, right? In class, quizzes will be there in the class, right? When you are in the class, quizzes will be asked to you. That means that just like I showed you the quizzes, leaderboard will be there in the class, that you can judge yourself that what is your level as compared to your competition, right? As compared to your peers, what is the level, right? How you more need to improve and focus on the class. Then previous year question, practice question, as I told you, the batch is starting from 29th of May, and that is at only at 3,999, that is available to you. You can see the link is in the description here. So this is our link here that you will see Sigma JEE Batch 2026. You can just click here, and that is for 12th and dropper students at this point, because holidays are going on. So the classes are in the morning, but after that the classes timings eventually are going to change, right? Because the school are ongoing, right? So we have to focus on those students as well, right? So don't worry, everything we are doing here, right? And regular sessions we take, right? In daily 3 to 4 classes will be there, right? On time sessions are being taken, not even 1 minute delay you will see by the teachers, right? And DPPs, everything, quizzes, that is the regular ritual of the classes, right? That is strictly followed by the teachers. So that is very beneficial for all the students out there, right? So that's it for today, students. And you can see if you have any doubt related to Sigma batch, you can comment down any problem you have. And don't forget to hit this like button here and see the batches that you have. You have already taken the demo session here, right? The same will be provided to you in the batch, right? So everybody, I'll see you all in the batch. And I'm very excited because in the batch we cover every topic in detail with the practice question with more interest. Like just now, we have completed photoelectric effect, Rutherford model, right, with all the simulations, so that you're not only reading the topic, you're absorbing the topic, right, so that you can learn or recall this topic at any point of time. No cramming, pure conceptual knowledge we are giving you here, right? So that's it for today, students. Bye bye. Take care. If you have any doubt related to Sigma batch, comment down, right? We are here to answer. Till then, bye bye. Take care.